invitation to speak. Speak here. So this is sort of, I guess, like pandemic themed or inspired problems. It's mostly going to be joint work with Duncan Dauvergne, who is a postdoc at Princeton, and now he's an assistant professor in Toronto. And I'll also mention some work with Dor Elboim and Nam, who are students of mine. Danny's graduated now, and he's working for actually not so far from you. He's at a hedge fund in Irvine. But okay, so particularly at the beginning of the pandemic, you may have heard epidemiologists talking about the SIR model, which stands for susceptible, infected, and removed. And so this is a sort of, and particularly when they were sort of discussing, what is the rate of growth of the infection, traditionally, this is sort of studied in the mean field sense, where essentially everyone can potentially infect everyone else, and so you can analyze it with differential equations and sort of say what fraction of the population will get infected. We were interested in sort of looking at the SIR model in a sort of interacting particle system sort of setting, where we have particles in the plane. I mean, all my pictures are going to be in 2 dimensions, but you could do this in higher dimensions too. So you have particles representing individuals in the plane. They're all sort of moving around independently, doing continuous time random walks. And initially they're all susceptible. And then we add at the origin one infected particle. And so when a susceptible and infected individuals meet, the susceptible one becomes infected. And so the infection can potentially spread over time. But the infected ones also get cured and become either removed or recovered. And we say that this happens at rate mu. And so this is just some simulations of different time shots of this process in the plane, and it's sort of the black ones are the susceptible particles, the red ones are the infected ones, and I'm not showing the removed ones. So you can see that the sort of infected region sort of spreads out over time, and leaving sort of a fairly empty space in the middle. But of course, it could also just die out. And so the basic question I want to address is, okay, at least if the recovery rate is fairly small, does the infection go on forever? And intuitively, it seems like it should, but you need to develop a reasonable amount of ideas in order to prove something like that. And I'll sort of describe how you can go about that. Maybe any questions? So if anyone has any questions as I'm going along about I guess anything I say, please stop me. And so this sort of fits into another class of models that's been studied more, that I'll also tell you some new results about. And these are go by different names. Sometimes they're called A-B models, and which basically would correspond to a susceptible type and an infected type. And so in this setting, nothing gets removed, and when a type A particle meets a type B particle, the type A one becomes B, i.e. infected. So now there'll always be infected particles, and you would sort of imagine that the infected region will kind of grow over time, as you see in these simulations. And initially, we're going to start things off with sort of the Poisson particles having, the susceptible particles or the type A particles having a Poisson density lambda. And since they're doing random walks, this will be like the equilibrium distribution. Now, you can also, the type A and B particles also don't have to do the same thing. We could have the healthier ones moving faster than the sick ones. So we could also have different speeds for the different types. Okay. I don't. Not. Having some small issues with changing slides, but okay. So probably the most important work on these models was done by Keston and Siderovicius, and they studied the case where the speeds of the two particle types are the same. And so in this setting, the type B, if you look at the set of infected particles, they showed, first of all, that it grows linearly in time. In a second sort of even more impressive work, this one is in the Annals of Mathematics. They showed that if you look at the set of infected particles, that it has a shape theorem. So there's some deterministic shape U that's convex and symmetric. And basically at time t, everything inside t times U is infected, and everything outside of it is susceptible, up to some 1 minus or plus epsilon factors. So this shape that we see here is basically tending to some deterministic shape. And this is something that we'd expect in all of these models. And so if you want to so why should we have sort of some linear growth rate? Well, if we think about the front of the infection, sort of the boundary between the infected region and the uninfected region, if there's a reasonable number of particles there, then soon there'll be a reasonable number of infected ones. And some will move to the left, some will move to the right, some will move up, some will move down. And at least some will be moving sort of in the way that sort of expands out the infected region. So as long as the infected region is moving through areas of typical density, it should be sort of growing at some constant rate. And essentially what Keston and Siderovicius proved was that it's going to spend, at least in their first paper, was that it's going to spend a constant fraction of its time in this areas that have a reasonable density of particles. And so the challenge is to show that the front doesn't spend too much time in very sparse areas where there's not many particles. And essentially they're able to do this because, and this is where their assumption that the speeds are the same is important, because when the speed is the same, if you just look at the particles without labels as being infected or not, then they're just doing independent random walks and it remains in equilibrium. So at any time t, the distribution of particles just looks like a Poisson process. And so you can calculate what's the probability that some region doesn't have very many particles in it. And you can also sort of study how this evolves over time. And so if you look at sort of space and time, you can sort of study what's the probability that some region will be sparse at some particular time. And essentially the sparse regions, I mean, they may remain sparse for a while, but they'll tend to sort of dissipate quickly, and the densities will sort of smooth out. So if you take some larger region, on average, that will have a sort of reasonable density, and then that will sort of spread out and average out fairly quickly. So these sparse regions are sort of rare and behave sort of like a very subcritical percolation. And from that, you can deduce that the front must sort of not spend much time in the sparse regions and and get a sort of linear rate of growth from that. On the other hand, the shape theorem is you need to say more than that, and they came up with a sort of very nice sort of approximate or distributional sub-additive or superadditive ergodic theorem kind of an argument that sort of said what the speed would be in each particular direction. Okay, so what happens when the speed of the different types is different? So their methods sort of didn't work in this case, and they were only able to prove a suboptimal result, that everything in a ball of radius t over log t is infected. But really, nothing should really change when we have different speeds for the different particles.
Are you going to tell us how you determine u? What, do you have an explicit computation of the geometry of u from the very little information you have about speeds?
I'm not, because really nothing is known about u.
Wow.
And that it's really the existence of it is shown from essentially an ergodic theorem, like a type result saying that in each direction there must be some speed, but that just shows that the existence of some speed, and you don't the proof doesn't tell you anything about what that actually is. So I think it's fair to say that the only things we know are that it's symmetric and convex. Yeah, I mean, even like really basic properties like, is it like is it smooth?
Is it connected?
Oh yeah. So I mean, it will be.
It could be a couple of.
I mean, it's a convex set, so it should be.
Yeah, I guess I was thinking you could get. Yeah, it probably has to. It has to be if it's convex from.
Yeah. So, but other than and symmetric about the origin, but other than that, really, that's it. But I mean, in the more general models, we don't even know the existence of such a shape theorem. So, yeah, there's really very little we can say. And I mean, it's sort of analogous to models of, say, first passage percolation, where, again, existences of shape theorems have been known for a long time, but very little is known about sort of the actual shapes that you get, except in like the exactly solvable last passage percolation models. Okay, so in this setting where the speeds are different, now the speeds of the walkers or the locations of the walkers are dependent on the infection process in some complicated way. The process also isn't monotone anymore, in the sense that if I added in or let's say made some new particle to be infected, then that particle that sort of changes its speed, so it may then no longer infect some other particle. So making some particles infected might lead to less particles being infected later on. And this lack of monotonicity is sort of rules or sort of precludes various strategies, unfortunately. But nonetheless, we sort of still expect that the front should move at a sort of nice linear rate, and that it should sort of keep encountering sort of fresh new particles that are more or less independent of the process up to that time. And so it should keep moving along at a reasonable speed, and then keep finding new particles, and then that will sort of keep it progressing. But how do you turn that sort of intuition to a proof? So I'm going to talk about first multiparticle DLA, which is sort of the analog of when the infected particles have speed 0. And there've been a couple of earlier works on that, and we use ideas from both of those. Okay, but to get to multiparticle DLA, I'm going to first say a few words about the classical model of diffusion limited aggregation, which is quite a famous model that probably many of you have seen before. And the idea is you have some aggregate and these are like the infected particles, and they won't move. And then we'll add in one more particle from infinity and let it sort of do a random walk or diffusion until it hits the aggregate, and then it freezes and becomes part of the aggregate. So it's just sort of growing one at a time. And if you keep this going for a long time, you get these very interesting diffusions. Sorry, what am I saying? These very interesting fractal-like objects that have this sort of tree-like branches going out in different directions. So this is the top picture is a simulation. The bottom one is a real experiment of electrodeposition in a copper sulfate solution that's supposed to be roughly modeled by this DLA process. So very little is known rigorously about DLA. And I think it's fair to say that almost any question you ask remains open. Every time I try and think about it, it's after half an hour, I feel very, humbled and frustrated. And I'm certainly not going to tell you any new results about it today. So instead, I'll tell you about a sort of variant of the process that initially might look more complicated, but is actually easier to understand. And this is multiparticle DLA. And so rather than adding one particle in at a time from infinity, we imagine that there's a sort of sea of like susceptible particles, or the type A particles, and they just sort of move around doing their own independent random walks until they run into the aggregate, and then they get frozen and stopped. And so this is like the AB model, except where the speed of the type B particles is 0. Except it's changed slightly because I say that they get frozen just before they jump onto another type B particle. Otherwise, they'd all be sitting in the same spot. So this is a simulation by Alexander Stauffer with a density of particles of about 0.3. And I don't know what the resolution looks like on your screens, but in the middle, it looks, at the beginning of the process, it looks quite like DLA. And at least if you start with a low density of particles, this sort of makes sense that you're sort of just kind of adding one particle occasionally, and it will be sort of growing like DLA. But over time, as it sort of grows, the shape that you get is becoming sort of more uniform, and it looks sort of plausible that there should be some limiting shape theorem for this model as well. We don't know that. What we do know, and there's two different proofs of this, one by me and another by Sidrovicius and Stauffer, that show that the speed at which the aggregate grows is linear if the sort of type A particles have a high enough initial density. And I want to tell you about both proofs of those, or at least a little bit about both proofs of those, because they both contain sort of ideas that we'll use for the general AB particle setting. So these just applied when we have a high density of particles. You may wonder what happens when we have a low density of particles. Does it behave differently? Is it more like DLA in that setting? And the conjecture is actually no, that for any density of particles, you should see the same kind of deterministic growth eventually. It will just be that for a longer period of, there'll be some sort of crossover where initially it looks like DLA, but on a big enough scale, the shape that you get starts looking essentially deterministic. But that's still another interesting open problem. Okay, and that's in dimensions 2 and higher. Actually, funnily enough, in dimension 1, you do have a phase transition or in the density, which is kind of a bit surprising because, you know, in a lot of mathematical physics models, they're sort of simple in one dimension, and then you get more interesting phenomena in higher dimensions. But here it's only in one dimension you get different things going on. So, so in one dimension, it's just particles doing a random walk on the line, and then when they sort of run into the aggregate, they get added to it. So now that the geometry of the aggregate is very boring, it's just a line segment, the only thing you can ask is sort of how quickly is it growing and how does that vary as a function of lambda? So Keston and Sidrovicius showed that when lambda is less than 1, it grows like square root of t. And the reason is basically there's not enough particles for it around to grow any faster. So if you look at, for it to grow length L, you need at least L particles, but initially you have a Poisson with mean lambda times L, which is usually much smaller than L number of particles. So you need to wait long enough for enough particles to get close to the aggregate. And because they're moving diffusively like random walks, you get the sort of square root of t as the right growth rate. And if you're more careful in work of Dembo, he worked out what the right constant in front of this should be by, which you can get from some kind of partial differential equation. On the other hand, in the supercritical regime where lambda is greater than 1, this you do get a constant, you do get sort of linear growth, and xt over t converges to some positive constant almost surely. And essentially the proof is saying that if the aggregate, if the rate at which it's growing starts to slow down too much, then there's a sort of mean reversion which pushes it back up again. Some kind of multi-scale analysis of this and a renewal process argument shows that you get a strong law of large numbers. And so it's square root of t for lambda less than 1, like a constant times t for lambda greater than 1. It's natural to ask what happens at the critical value of lambda equals 1. Oh, but before I get to that, I want to mention that actually, so this analysis was done in the case of it's for one dimension, but actually it extends to higher dimensions because if you look at the aggregate and look at the location of the rightmost particle of that in higher dimensions, you can couple that with the one-dimensional model and show that it's growing at least as quickly. And so actually you can show in, say, 2 dimensions, whenever lambda is bigger than 5 over 6, that you get sort of a linear growth rate. Okay, and so now in the critical case where lambda equals 1, the predicted speed was that it grows like t to the 2/3, and with Dor and Danny we showed this and worked out what the right scaling limit as well. So when you rescale by t to the 2/3, it converges to the integral of a diffusion, where the diffusion is given by this stochastic differential equation. So dRt equals 2RT to the 5/2 dBt. And this was interesting because I feel like in most work that I do, I sort of always know what the right theorem should be at the beginning of the project. And then it's just a matter of, can you prove that? And so hopefully sometimes you can. But in this case, this wasn't something that we guessed at all at the beginning of the project, and it was something that we really discovered as we went along. So that was fun. This SDE is a -1/3 self-similar process, so it satisfies this scaling relation. It's also a Bessel process to the power of -2/3, which was a bit of a surprise to me, although it really shouldn't have been, because I know here's a fact that was in textbooks, but I didn't know it, and a sort of very unscientific survey of other probabilists I've chatted to, most also didn't know it, and that is, if you have a diffusion and it's self-similar, then it must be a power of a Bessel process. And the exponent of -2/3 here was sort of determined by the right scaling law. The dimension of the Bessel process, 8/3, I don't have as good an explanation for, except that it's the only dimension that would give you that RT is a local martingale. So there's no drift term here. It's not a martingale because it tends to 0 almost surely, but it's a local martingale. So that's the description of what happens in the critical case. Okay, and I want to say a little bit about the proof. And the main idea is that we want to sort of, xt, the length of the aggregate, is like it's a jump process, and it has sort of at each time some infinitesimal jump rate. And so you could ask, what is that conditional on its past? So and that's basically related to what is the density of particles sitting right in front of the aggregate. And it turns out that if you condition on the past of xt, the number of particles sitting in front of it is still Poisson, but it's Poisson with a different mean. And the reason why it's Poisson is that we can think of, initially we have sort of the locations of the particles are sort of Poisson, but we could have also thought of it as the initial locations and future trajectories of the particles are Poisson. So it's like a Poisson process on path space of particles. And then the particles sitting in front of the aggregate are just the ones that end in front of the aggregate, and before that avoided the aggregate or stayed to the right of the aggregate up to that time. So if I write the yt is the time reversal of the aggregate, then this infinitesimal jump rate is just given by lambda over 2 times the probability that a random walk is less than or equal to this time reverse process. And because the time reverse process is random, that's a random process. And we can study its evolution and show how that grows over time. And in the critical case, locally, it turns out it behaves quite like a continuous, or like a critical branching process with continuous edge lengths. And we were able to sort of study that and work out what the right stochastic differential equation that it converged to. Okay, but sort of the key idea here was that we don't want to study all the particles, all the moving particles. We just want to say that given the aggregate up to some point in time and conditioning on that, the number is Poisson in some way that we can calculate or bound. Okay, so the other sort of proof, and this is by Sirius and Stauffer, looked
Question?
Oh, yeah.
On the previous slide, I'm confused by the inequality in your definition of S of t, because the S is a parameter in the inf.
Oh, that's a little s, I guess.
Oh,
Lowercase s. So essentially so if I want the so if I want the speed at time t, I sort of reverse time from time t. So s runs from 0 up to t.
yeah.
And then I want some random walk to always be less than or equal to that. And
So it means that yt of s is bigger than w of s for all s less than or equal to t.
yes.
Okay.
Yeah.
All right.
Yeah.
Thanks.
Yeah, and and at least so if things are behaving in a sort of fairly regular way, if the speed is sort of fairly constant, then yt is like a biased random walk, and so you're asking, and so yt minus, or y minus w is like a biased random walk, and you're asking the probability that it always stays above 0. But I don't know, we needed, for the critical case, we needed about 130 pages to analyze this. So it was, I don't know, by having one slide about this, I'm sweeping a lot of things under the rug, but yeah. I don't know, any other questions about? Okay. So Sidorowicz and Stauffer looked at sort of the exclusion process version of this model, where you're only allowed one particle at each vertex. So they're doing random walks, but they don't jump onto another particle. And they looked at the case where the density was close to 1. So almost every site has a particle in it, and there's just occasional holes. And so you can really think of the holes as doing almost like random walks in the sea of particles. And they sort of developed a multi-scale analysis to sort of show how the holes will be surrounded. So this is a picture I stole from their paper. And so these little circles are empty circles of the hole, and the black disk is supposed to be the aggregate. And essentially it should just sort of keep growing nicely, because the boundary, because almost everything is a particle. But then occasionally it comes across a hole. And what they showed was that it's likely for the aggregate to sort of quickly surround a hole and sort of keep moving on. But then sometimes it will encounter a few holes at once, and then it sort of needs some bigger radius in which to surround them and keep moving on. And then sometimes it has sort of one collection of holes and then next to another hole, and then in this region you need sort of an even bigger radius to surround. But they come up with a sort of systematic way in which to study it, and they do that by introducing another model that they called first passage percolation in a hostile environment. And this is sort of a competing growth process. So there's red particles and blue ones. The red one will just grow at rate 1, so it will spread to its neighbors at rate 1. The blue process spreads at a slower rate, at rate theta less than 1. But the blue process also starts off sort of with some low density in the whole plane. So for each location, it has a probability epsilon of being a blue seed. But they don't start growing straight away. They only start growing when the red process tries to expand onto that. So initially the red process is growing, then it tries to jump onto this blue one, and so then the blue process there starts growing as well, but the red one is growing faster, so there's a good chance of it sort of quickly surrounding the blue process. But then, later on it could run into several blue ones at once, and so then it has to work harder to sort of take over and surround those. But nonetheless, Sidorevicius and Stauffer showed that if the initial density of blue seeds is small enough, then there's a positive probability of the red process basically taking over most of the plane and sort of growing linearly, and essentially the blue ones being only a small fraction of what survives. And what they also showed was that if you can compare this to the multi-particle DLA and show that the aggregate is essentially growing at least as quickly as the red process. So the aggregate is stochastically dominating the red process here. Okay, and so the way they did this was by saying that, well, if there's just a single blue one sitting there, then as long as the red one is starting sort of far enough away from it, it will be able to sort of surround all but sort of some bubble around the blue one. So let's draw sort of bubbles around each of these blue seeds. But then sometimes these blue seeds are sort of close together, and the red process would, and one will sort of slow the red process down surrounding the other. So we might need to put those in sort of level 2 bubbles. And then sometimes those level 2 bubbles are next to each other. So we might need a level 3 bubble, and so on and so forth. And they had had some multi-scale scheme to cover all of these seeds in these bubbles, and they showed that everything outside of the bubbles gets taken over by the red process. I mean, as long as the red process is in the infinite component of that, of the complement. There is, of course, a chance that initially the red seed is just completely surrounded by blue ones, and then in that case, certainly the blue wins. And they also showed that the fraction of things covered by these bubbles is a fairly low density if epsilon is small enough. And so we want to use this same kind of analysis to show in the AB model that it's spreading out at a good speed. And so in the next next I want to describe sort of how we do that. Any questions before I go on? Okay. So we're going to do things by essentially taking a coarsening of the plane. So we'll split the plane into boxes of side length L, and we're only going to sort of reveal what's happening in a subset of the boxes. And so we're going to sort of color them over time, red and blue, and this is supposed to be the like analogous red and blue to Sidorevicius and Stauffer's process. And essentially the rule will be that a box will be colored red if an infected particle enters it, and it will be colored blue if the box has been sitting next to another colored box for enough time, say about L squared. So we start the dynamics, the particles are sort of doing their walk, then an infected one enters a neighboring block, and then they get colored, then we discover sort of what's happening to new particles, and it's sort of, the colored region keeps growing over time. These two blue boxes were shaded blue because they'd been next to a red one for enough time. But we only observe particles that have been in the colored region up to time t. And the reason for that is it sort of makes what's happening outside of this region independent, or not exactly independent, but retain some independence. And so the way we'll do that is when a box becomes colored, I want to sort of have decided in advance what we're going to find there. So on the right, I have sort of like a Poisson process on the plane, and we sort of will just decide this at time 0, and that's going to tell us what we should sort of discover when a new box is discovered. So this is the first time that a box is, the box to the right is colored. And so we look at the corresponding box on the right. There's one particle there, so we copy that on the left. And then, and now 2 more boxes became shaded red, and they had these 2 particles here on the top one on the left correspond to the 2 particles in the corresponding box on the right. And so we just sort of keep evolving the process like that, and that sort of gives us a way of constructing this restricted view of the process, but lets us sort of say what's happening in each of these newly discovered boxes is sort of independent of what we've discovered so far, except that it shouldn't really be independent. So I'm sort of there's something missing in this description, which is that we need to which is that when you color a new box, you need to only reveal particles that haven't been in the colored region before that time. And so we need to take that into account in this construction. And so here's so in this view, sort of space is on the x-axis and time is on the y-axis. And so each column would represent a block. And so imagine at time t, this block gets colored for the first time. So we could generate a Poisson process for that block, but this doesn't take into account the fact that the particles had to have avoided the colored region up to that time. So I can map the shaded region across, and now I'll also generate past and future trajectories for each of these particles as independent random walks. And 2 of those trajectories go through the colored region. So, so those ones shouldn't be there. So we just remove them, and we're left with particles whose past trajectories didn't enter the shaded region. So these ones we keep and add them to the process. And their future trajectories we use for sort of what they do in the future. So this is a way of constructing this process, and it's done in such a way that we're just sort of adding, or you know, we can construct this what we find in box B at the beginning, and this gives us sort of more independence to work with. And so how do we relate this to the first passage percolation in a hostile environment setting? Well, we have to define what are the bad boxes. What are the ones where the infection isn't going to spread to its neighbors quickly? So I'll tell you what the complement of being a bad one is, so what it means to be good. And that's essentially that regardless of what the history of the shaded region looks like, we're still going to see lots of particles in that box. And wherever an infection enters in the boundary of the box, that's going to infect a lot of particles from that box quickly, and then they're going to quickly spread to the neighbors and infect those. So it's blocks that, regardless of how they first get infected, will quickly infect their neighbors. And what we can show is that if L is big enough, the blocks have a very high probability of being good. One tricky thing, or one thing you might worry about, is we have to do this sort of over any possible shaded region. But there's really a maximal size of that the shaded region can be. And this is because of our rule that if a box has been next to a shaded box for time L squared, then the shaded region has to spread to that box. So from the point of view of one box, at the time it gets shaded, it sort of blocks at distance k from it can't have been shaded for more than time k times L squared. So then we just look at particles that avoid this sort of worst case shaded region. And yeah, and so we can show that the probability of a box being bad is low. And so using and then we can couple it with first passage percolation in a hostile environment and show that essentially the red ones, which will correspond to being the ones that got shaded by being infected, that this spreads out at some linear rate, and most boxes get shaded like that. And that there's enough infected particles around that they quickly infect any nearby ones. Okay, and so we're able to prove the analog of Keston and Sidorevicius's first theorem for speeds which are different, so that the particles, the infected region grows at a linear speed. And this happens with high probability. The first passage percolation in a hostile environment fails with a positive probability, but we sort of show that if we take the block size big enough, then we can make that probability arbitrarily small. But that in turn reduces the speed of the process. So we have some kind of system where we start off with big blocks and then sort of gradually work down to smaller blocks. We don't know a shape theorem. It must be true, but yeah, our methods don't establish that because we don't have any sort of nice superadditive properties. And now getting back to the SIR model that I began with, we can apply the same sort of analysis there too, as long as the infection rate is small enough. So then, and in that case, we need to choose the block size L as some function of the infection rate, sort of, so that it's small enough, the block size is small enough so that typically there won't be many healing events before the infection has spread through that block. And so with positive probability and tending to 1 as the infection rate, as the healing rate tends to 0, the infection survives forever and grows linearly. And it's sort of interesting, so that you really divide the plane into sort of 3 different regions. On the outside, you have just sort of all susceptible particles. On the inside, it's pretty empty. And the infection is really in just sort of a very narrow one-dimensional almost space. So it should really be only about, like the infected region should only really have a width of at most log t, and really in most places just of a constant order. You can ask what's happening in the middle, and you get sort of a herd immunity regime. So you get a low density. So in the middle, there's no infected particles because there's not enough susceptible particles to sustain an infection. But there is a small number of a small density of susceptible particles that's like a strictly positive. And these are the ones that sort of manage to socially distance their way through as the infection front came. avoided getting infected, then the infection front moves past them. Soon there's not many or very few infected particles around, and so they just manage to survive and be susceptible forever after that. So this is a sort of simulation of that. It was kind of surprisingly hard to tune the parameters to actually get a picture that matched the statement of the theorem, because if you set the healing rate to be too high, then the infection dies out, and if you set it to be too low, then there's too many infected particles, and it's too hard for a susceptible one to not get infected. So there was very few particles in the middle. So, anyway, so that's so the density of particles left over is probably fairly small in general. Yeah, that's it. So thanks for listening, and let me know if you have any questions.